Let's now take a deep dive into the kinematics and dynamics of a charged particle injected at an angle into a region of uniform magnetic field and subsequently undergoing motion along a path that we would describe as a helix or a helical path. Okay, so suppose here we've got a magnetic field coming out of the page, uniform B field. So B is the magnitude of that field. That'll be a positive constant pointing in the k-hat direction. So we're looking down at the x, y plane here, B coming out of the page. And our particle will be given this initial velocity. So it has an initial y component, but also an initial z component. So it's actually tilted up out of the plane of the page, coming out like that from this point of view. Or we could rotate this diagram 90 degrees to have our z-axis, which is right now pointing straight out, have that z-axis rotated pointing right instead. That's this picture over here. So here's our magnetic field pointing in the z direction. Y direction is still up. From this point of view, the x direction would be into the plane of the page. Okay, so from this point of view, we see we have that initial z component to our velocity as well as that initial y component to the velocity. This particle will be subject to a magnetic force given by this formula. So if we want to express V in terms of its components, Vx, Vy, and Vz, which will all be functions of time, so this could be V at any point in time, then we're going to cross that with the magnetic field vector, which is a constant with time. Okay, so the cross product can be found by evaluating the determinant of this 3x3 matrix. Or if you're not familiar with this method, which is fine, you could just distribute across this cross product here. So the I hat term crossed with the k hat term plus the j hat term crossed with the k hat term plus the k hat term crossed with the k hat term. Either way, you'll get to this expression for the magnetic force, which will have an x component that depends on Vy as a function of time, and the magnetic force will also have a y component that depends on Vx as a function of time. Let's go now to Newton's second law. We've got our force components, so now we can write down our acceleration components. Ax is dvx dt is fbx over m, and likewise for the y and z components. The x component of the force, fbx, let's see, that'll be this right here, qb times vy, so qb vy over m. The y component of the force is given by qb times negative vx, so negative qb vx, there's our y component. And there is no z component to the force, so there's no z acceleration. The particle's velocity in the z direction will be constant. Okay, so now we would like to find the velocity components as functions of time and eventually the position components, x, y, and z, as a function of time, as functions of time. So to do that, I'm going to try a little trick here. I'm going to look at the second of these three equations and take the time derivative of this whole equation. So day dt will be equal to d squared vy dt squared. Skip this term, go over here, and we want d dt of this. qb and m are constants, so it'll be minus qb over m times dvx dt. Okay, so this is what we've gotten from taking the time derivative of the second equation. And now note, it depends on dvx dt, which is a term that also appears way up here in Newton's second law. dvx dt is just ax, so this term is just ax, which is given by this here, qb vy over m. So I'm going to sub that into here, and so we have the negative qb over m times qb over m times vy, which comes to negative qb over m squared times vy. And now note what we have. We have the second time derivative of vy equals the opposite of some constant times vy. And that is the exact form for simple harmonic motion. Whenever we see an equation like this, where d squared dt squared of some variable equals the opposite of some constant times that same variable, we know that that variable will be a harmonic function of time. It can be expressed in terms of sine and cosine functions like this, where that constant is related to the angular frequency of the oscillation. So we're seeing here that Vy is like our x, and this here, QB over m, that's our omega. So Vy is going to be a harmonic function of time. So Vy can be expressed in terms of sine or cosine functions. To figure out which is which, let's go up to our diagram here and look at our initial conditions. Vy is initially positive, and we see that the force that we're feeling at this initial moment will be V cross B. So V is up, B is out of the page, so my thumb points to the right. Our initial force will be to the right, and we can tell that this particle is going to be undergoing circular motion along a path like that. There's our uniform circular motion here. Okay, so Vy is initially at its max value and will begin immediately to decrease. Therefore, we can conclude that Vy can be given as a cosine function, cosine omega t, where omega is given by this here, QB over m. So that's 2 pi times the frequency, or our frequency is our charge to mass ratio times B over 2 pi. We have recovered the formula for our cyclotron frequency. So we see this particle is going to be circulating in this field in a clockwise fashion with a frequency given by this, the cyclotron frequency. Okay, let's get Vx as a function of time. We can do that by going through a similar argument, starting from this equation, taking its time derivative, substituting this in for dvy dt, and discover that Vx also obeys an equation of this form. So Vx is also a harmonic function. Matching its initial conditions, we see the initial Vx is 0, and then Vx begins to increase from there. So Vx can be given as a sine function. And its amplitude of that sine function will be equal to the amplitude of the Vy function. That omega is, again, this omega here. It'll be the same omega. Vz as a function of time is just a constant as previously noted, since no magnetic force in the z direction. And now, with our 3 components of the velocity, we can find the 3 components of our position, x of t, y of t, and z of t. We know that Vx, Vy, and Vz are just the derivatives, dx dt, dy dt, and dy dt, and dz dt. So we integrate these 3 functions to find our 3 position functions. So in this picture, I suppose we can imagine an origin that will end up being at the center of this circular path. So our initial x-coordinate will be over here at this negative location. Our initial y-coordinate will be 0. And let's say that in this initial plane, this is the z equals 0 plane. So initial z could be 0. So those can be our initial values here. X will be negative. What we'll discover is the gyro radius. We're about to get to that. Integrating this function, we find that x of t can be given as minus v naught y over omega times cosine omega t. So at time 0, x is initially at its negative max value. At time 0, the x-coordinate is over here at its negative max value, if that's our origin, right in the middle. Okay, so v naught y over omega, that will be the sort of amplitude of this oscillation, which will be the radius of that circular path. V naught y over omega, we know that omega was qb over m, so plug that in, and we've recovered our expression for the gyro radius, noting that the speed that it actually depends on is the y component of the speed, or the component of the velocity in the in the plane perpendicular to the B field. And that's our gyro radius, RG, right there. Likewise, the y component of the position as a function of time can be found by integrating this function, which gets us this. It'll be a sine function since at time 0, y is 0. Again, v naught y over omega is our gyro radius. And then z as a function of time is just this linear function since v naught z is a constant, or since vz is a constant. We can let z equal 0 at time 0 to get that. And so we see that we will have that x will be a harmonic function of time. X is oscillating like this with a frequency equal to the cyclotron frequency, just as y coordinate is oscillating like this with a frequency equal to the cyclotron frequency, and the combination of those gives us our uniform circular motion in the xy plane. While at the same time, the particle is drifting in the z direction. So just as it's circulating like this, it's also drifting outwards like that. So the combination of those two will be a spiraling path. That's our helix. From this point of view, we're launched in this direction, so we'll be drifting in the z direction while oscillating in the y direction. So we'll be oscillating in the y direction, drifting in the z direction. There's our helical path. Got one more drawing of that down here. This is the same image as above, as this picture here, the y-z plane. So here in the z direction, the particle will be drifting just as it's oscillating in the y direction with an amplitude equal to that gyro radius. The x direction would be into the page from this point of view. Now the distance in the z direction, the distance parallel to the B field, called our B field, is in the z direction. The distance the particle drifts parallel to the B field in the course of one full cycle. So the distance in the z direction the particle moves while completing one orbit is known as the pitch. The pitch of our helical path. This is a helix here. The pitch of that path is that distance it travels in one period. So pitch is the delta z over one period, so v naught z, and put in the period for time here. The period is the reciprocal of the frequency. There is our cyclotron frequency. So v naught z, our z component of the velocity, the component of velocity parallel to the magnetic field, times this gives us the pitch of our helix, how sort of stretched out our helical path is. So there you go. There's a great exercise in skills from mechanics, starting with Newton's laws and integrating to find velocity functions and then position functions, and applying initial conditions to relate harmonic motion in 2 dimensions to uniform circular motion, adding now in the helical drift.